Okay, have you ever just stopped and wondered what holds literally everything together? I mean, the chair you're sitting on, the air you're breathing, you. Well, today, that's exactly what we're going to do. We're peeling back the layers of reality to look at the fundamental rules that run the whole show. Let's dive in.
We're about to go on a pretty wild journey. We're going to zoom in from the familiar stuff all around us, right down to the absolutely mind-bendingly powerful core of a single atom. It's a story about the bonds, the personalities, and the insane energy that makes our world exactly what it is.
So, first things first, let's start with the basics, the fundamental architecture of our universe. What actually gives matter its shape?
I mean, really think about it for a second. Why is water, a liquid, and a rock a solid? Why do things have the structure they have?
The answer? It all comes down to the chemical bond. You can think of it like this elegant, invisible dance between electrons, those little particles buzzing around the outside of an atom. The way they interact with each other is what creates the incredible variety of everything we see.
So how do we predict the shapes these bonds are going to make? Well, scientists have this model with a mouthful of a name, VSEPR theory. But don't worry about the acronym, okay? The main idea is actually super simple. Electron pairs are all negatively charged. So, just like trying to push the same poles of two magnets together, they push each other as far apart as possible. That's it. And check this out. This table shows exactly how that pushing and pulling works. So let's look at beryllium fluoride. See? It's got two pairs of electrons and bonds, and no free pairs hanging around. To get as far apart as they can, they just form a straight line. Simple. But now, look at water, H2O. It also has two bonding pairs, but, and this is key, it also has two lone pairs just sitting there. Those extra pairs push down on the bonds, bending the whole molecule into that famous V shape. It really is all about that simple repulsion.
So, the takeaway here is that simple rule of repulsion. It's the invisible force that's sculpting our world at the tiniest level, from the double helix of your DNA to the properties of the plastic in your keyboard.
Okay, so if VSEPR theory gives us the architectural rules, what about the building blocks themselves? Now we're talking about the elements. And trust me, each one has its own unique personality.
You see, every single element on the periodic table has a kind of personality, and it's all defined by how its electrons are set up. Let's take a look at Group 1A, the alkali metals. As you can see from this data, they all have just one lonely little electron in their outer shell. This makes them incredibly generous. They are just dying to give that electron away to form a nice stable bond. And that's exactly what makes them so reactive.
And this personality basically defines everything about them. Because they lose that outer electron so easily, they are super reactive and just love to form strong bonds. You can kind of think of them as the most eager-to-please elements on the whole table.
Now, if you want to see a complete personality shift, just look at another group, like 5A. As you go down that column, you go from nitrogen, a gas that makes up most of the air we breathe, all the way down to bismuth, which is a dense, brittle metal. It's a perfect example of how the same basic rules can lead to wildly different results.
All right, now we're going to take a huge leap. We've been talking about the electrons on the outside this whole time, but what happens if we ignore all that and dive straight into the very heart of the atom, the nucleus? Well, let me tell you, the rules of the game change completely.
And this is where the scale just explodes. Look at the difference. A chemical reaction is like shuffling the furniture in a room. You're just rearranging the outer electrons. But a nuclear reaction? Oh no. That's like changing the very foundation of the house itself. You're altering an element's identity. And the most staggering difference? The energy. One is a spark, the other is basically a star.
Which brings us to one of the most powerful and frankly awesome processes in the known universe, nuclear fission.
It all starts pretty simply, really. You take a big, heavy, wobbly nucleus like uranium-235, and you just flick it with a single tiny neutron. That one little tap is all it takes to push the whole thing over the edge, making it incredibly unstable.
And then the magic happens. The unstable nucleus splits apart into smaller elements. But, and this is the crucial part, it also releases more neutrons. Each of those new neutrons can then zoom off and strike another uranium nucleus, causing it to split and release even more neutrons. It's a cosmic domino effect, a chain reaction that just builds and builds, releasing an immense amount of energy at every single step.
So how much energy are we talking about? Well, the energy from converting just one of these tiny atomic mass units is 931 mega electron volts.
To put that in perspective, that single conversion releases millions of times more energy than the chemical reaction of burning a molecule of TNT. It is a truly staggering amount of power locked inside the tiniest bits of matter.
And this is where we humans get clever. By carefully controlling that exact same explosive chain reaction inside a nuclear reactor, like this Daba plant right here, we can harness that incredible power to light up our world. We've actually learned how to tame the atom.
So there you have it. We went from the simple little pushing forces that shape molecules to the unique personalities of the elements, and all the way to the awesome world-changing power hidden inside the atomic nucleus. It really makes you wonder, what else is waiting to be discovered inside the building blocks of our reality?